Hello, my name is Martin Lukak, and today I want to talk to you about our joint work with Professor Khaled Al-Faqih from American University of Sharjah on the problem of length of the distinguishing sequences of reversible finite state machines. Now, finite state machines are essentially state transition systems which have a finite number of inputs, finite number of outputs and states, and have a finite number of transitions that are essentially labeled by some input-output pairs. Now, these systems are generally used in various areas such as software engineering, digital computing, games, or analysis and simulation of logic, and in particular they are very famous for being tools of design and verification. Because they have certain usage, or because they are quite useful in classical logic, it is also perhaps it is expected that their generalization to different computational paradigms are also useful. And therefore, in this work, we are looking how the length of the distinguishing sequences of these machines actually evolve for systems such as reversible finite state machines. So now, finite state machines essentially are specified by a sextuplet of given by a set of states, an initial state, a set of inputs, set of outputs, and the two functions. One of them is the next state or state transition function, that from a set of from an input and state gives the next state, and the output function that again from a state and an input gives the next output. Example of such a general machine is shown in table A, where you can see for given state A and 0, I, for example, have next state B and and output 1. Now, reversible finite state machine is a generalization or restriction on these machines, such that essentially we formulate them using a reversible function, with input S and X that has outputs S bar and Y. And because it is a reversible function, the inverse f minus 1 applied to S bar and Y will give us S and X, right? So such a reversible function, a reversible finite state machine can be seen in table B, where we can see that for any combination of state and input, we again have a combination of state and output. However, in this case, every combination of state and output is unique, and therefore the inverse is possible. Now, as we were discussing, one of the advantages of finite state machine is their ability to actually do or being used for verification. One of the tools for verification called is actually a distinguishing sequence. Now, the distinguishing sequence is a sequence of inputs that, when applied to a machine, will lead it to a set of distinct states. Now, this essentially means if I have a machine in an unknown state, represented by all possible state A, B, C, D, and I apply a sequence 1, 1, 1, it will lead to states A, B, C, D uniquely identified by a sequence of outputs. Therefore, if I didn't know when my finite state machine was here at the beginning, by observing the set of outputs, I can say exactly in what initial state this machine was. Now, this is one of the more important sequences because it allows to do debugging, it allows to do whether it is machines or it is code, and so on. Okay, so before proceedings into looking in these distinguishing sequences, we define a reversible machine which is called output balanced finite state machine, and it is such a machine that for every input it has a balanced assignment of output values. So for instance, as you can see, for output 0, this machine has a output assignment 1, 0, 0, 1. For input value 1, we have the assignment again 1, 0, 0, 1. So this is a balanced finite state machine. Yes? On the other hand, in table B, as we can see, the assignment is 1, 0, 1, 1 for state for input 0, and 1, 0, 0 for input 1. Therefore, this is not a balanced machine. Okay, so now we will consider such as reversible balanced machines, and we will separate them in 3 particular groups. Now, these particular groups, we will see them one after another. The first particular group of output balanced RFSM is such that number of states is equal number of inputs and is equal number of outputs. So, for instance, in table A, we can see this is an output balanced reversible finite state machine that has 3 inputs, 3 outputs, and 3 states. Now, as for the length of this machine, this is a very specific case, very unique to reversible output balanced state. This has a distinguishing sequence equal of 1 because the number of inputs is equal number of outputs is equal number of states, and for every input we have to have a balanced distribution of outputs. Therefore, per consequence, this is a machine that can be debugged in a single step. Yes. Now, a little bit more complex is a machine where the number of states modulo number of inputs is equal 0, which means the number of states is a multiple of number of inputs. So as we can see, for instance, here we have 4 states, 2 and 2 inputs, or here we have 6 states and 3 inputs. Now, because all of them are balanced, it now means that again, for every input, we will have a distribution such as 0, 1, 1, 0, 0, or we have 0, 0, 2, 2, 1, 1, and so on. So we have again a balanced function. Now it turns out that the length of the distinguishing sequence is at most the number of states divided by number of outputs. So for example, if I have 3, so here it will be 6 divided by 3 would be 2, times the number of outputs plus 1, which is essentially, in this case, is essentially 7. Now this is because what happens is at maximum we create here a group of a particular width, and then what we know is that when we are going to apply an input, all of the groups simultaneously will be either transformed or broken apart, and it turns out that looking a little bit deeper into how this dynamics works, it turns out that at maximum it can be the number of groups times y for each of them, because if there is one group that breaks that breaks all the outputs, then the most distant one is essentially the y times from it, s divided by y times from that target destination. Now finally, the type 3 for this output balanced reversible finite state machine is such a machine where the number of states modulo x is not equal 0. Now this essentially means that we cannot construct a output balanced machine, because it means that at least for one of the outputs, the number of states won't be the same as for all other ones. Therefore, there is no output balance function for s modulo x larger than 0. Now, the second type of machines is, of course, we had output balance. Now it will be output unbalanced reversible finite state machine. Now the idea is that for every input we don't have a output balance assignment, and we again break them in these 3 groups. However, to make the analysis a little bit simpler, in addition we introduce 2 specific cases, and this is a case where we say that for a particular assignment, the largest group with the same output has at maximum 2 states or has more than 2 states. So let's have a look. So the first machine that we look is number of inputs is the number of inputs is the same as the number of states, and it is such a machine where at maximum for next assignment for one particular output, at maximum 2 states are within such a group. So for example, here we see AB has 0, 0, EB has 3, and so on, right? So at maximum it is 2. Now it turns out that this is actually similar to what we saw before. Essentially, the idea is that in this case, the largest or the longest distinguishing sequence is the number of inputs, which means number of inputs minus 1 times number of groups. Yes. So this is very similar to what we saw before. Essentially, if we say that each of the groups can be either moving, essentially can be renamed without being broken, at maximum it can be done essentially y minus times the number of groups. Yes. So for each group, let's say I do at maximum k minus y minus 1 times, and because I have k groups, this guy can travel here, and finally will be broken. So therefore it is number of outputs minus 1 times number of groups minus 1. The second case is essentially such that, again, we have number of states is equal number of inputs, but in this case we have arbitrarily large groups. Now, what the main observation here is that the length of the distinguishing sequences for this machine increases at the rate of y, essentially by adding every time one element into the largest possible group, right? And so by observing this, we can start by 2, we add by 3, and so on, and it turns out that the largest possible or the longest sequence in this particular case is the number of states divided by the number of groups, yes, times y. So for example, this one has 2 groups, so it will be in particular, so this is I think uppercase, so this will be 3 times y, so in this case it will be up to maximum 15, yes? And so for the proof, please look at the paper. It essentially involves going from case of size of group 2 and adding one more input and observing what is the worst possible case. The second, essentially type 2, is essentially when the number of states is larger than x, and the first case is such that s modulo x is equal 0. Now this is the opposite to the case where we don't have the output balance machine. Here we don't have the output unbalance because all machines such that s is larger than x, and the number of states is the number of inputs is a multiplier for number of states, and in particular the largest group that is created by next output transition has value 2, means that we cannot have an unbalanced machine. Yes? So by default there is no such an unbalanced machine. Now the case 2, we have machines, and in this particular case we can essentially observe again that similarly to before, also here the distinguishing sequence increases by 1 by always adding one more state to the largest group k, and therefore similarly to before, we have the longest distinguishing sequence is the number of outputs, which is y, times number of states minus the number of groups. Yes? Okay. The last group that we have is the type 3. Now the type 3 in case 1 is essentially is identical or is very similar to the type 1 case 1, which means where the number of inputs is equal to the number of states. But in this case, essentially, it turns out that the only difference is that the y is smaller than s. However, the distinguishing sequence is similar to the case 1, which is y times number of groups minus 1. Finally, the last case that we have is essentially case where number of states, number of inputs is completely unrelated, and the largest possible groups can have, for the next assignment of outputs, can have arbitrary value. And it turns out, again, doing a similar analysis to before, is that in this case it is again number of states minus minus the groups, minus the number of groups times y. Right? So essentially the idea is taking the largest group that exists and determining the distinguishing sequence essentially will always include inside any smaller groups any separation of any smaller groups. Okay, so in this paper we consider these various cases of reversible finite state machine, and we show that there are some specific cases that can be either very effective for determining distinguishing sequences, or there are finite state machines who actually don't have, that do not exist for a specific restriction of inputs and outputs. And finally, we also shown that most of the for most of the combination of reversible finite state machine, the length of the distinguishing sequence is shorter than the one which is defined by Kohavi for standard finite state machine. So therefore, it will be interesting to see how the application of the reversible finite state machine is cost-wise effective or ineffective compared to classical irreversible finite state machines. And in the future, we plan to extend the concepts to, in particular, energy conservative RFSMs, as well as to synchronizing sequences. So thank you very much. And if you are interested, please do not hesitate to ask me questions or consult our paper. Thank you very much.